You're welcome to another edition of Subject Math. Today we'll be talking about binary operation. Now, I hope we all know binary operation is not a new thing to you. Aside from that, this binary is quite different from your binary numbers. So please be rest assured, please know it clearly that there's a big difference between binary number and binary operation. Now, having told you a little about binary operation, now a binary operation is any rule. Please, I'd like to specify. Now, a binary operation is any rule of combination of any two elements of a given non-empty set. Now, whenever you are dealing with binary operation, you are not dealing with empty set. If the set is empty or if the set is null, you are not dealing with binary operation. Now, it is called binary operation because you are dealing with two non-empty sets because it is binary. And when it comes to binary gives us the concept of 2 as a number. Whenever we get to hear about binary, we get to talk about the number 2. Now, so talking about binary operations and the number of deal with the combination of two elements of a non-empty set. Now, let's proceed. So a binary operation is usually denoted by different operators. So we can have the asterisk, we can have the degree, we can have the multiplication, the addition, etc. So we can have different symbols to denote binary operation. Now, there are different properties of this binary operation. We're going to be dealing with the properties one after the other. Now, so these properties, we have the closure property. Well, I'm going to talk about these properties one after the other. So I would like us to know these properties first before we start the explanation of the properties. So we have the closure property. We have the commutative property. We'll talk about the commutative law of addition, the commutative law of multiplication. We're going to talk about that. We have the associative property. We have the distributive property. And we're also going to talk about the identity element, so as the inverse element. And we're going to cover these properties and some various examples throughout the properties before we round up the class. Now, look at talking about closure properties. Now, first and foremost, what is this closure property? Let's talk about its definition. Now, the closure property says that, or a closure property is a non-empty set S is said to be closed under a binary operation asterisk. If A comma B is an element of S, then A operation A asterisk B is in S. Now, what is this trying to say? If I have a number from 1 to 5, if I have a number from 1 to 5, the number can be expressed as 1, 2, 3, 4, 5. Now, if I say this should be my binary, or this should be my operation, now, it being closed means that every number or every operation is taken from this particular set of number. If all my whole operations, if all my whole questions, all my whole answers revolve within this range of 1 to 5, that means it is closed. But if I go outside this and go and pick a number 6, it is not closed. For example of a closed property is your wall clock. No matter whatever your wall clock is doing, it revolves the number between 1 to 12. It revolves within this range of numbers. So that is what a closed property. It can leave that 1 to 12. Now, from there, I have a straight question from my work, which says a binary operation asterisk is defined on the set R if real number, a set of R of real numbers by S asterisk Y. Now, this is very important. Define S asterisk Y is equals x squared plus y squared minus 1 for all x comma y that exist in R. determine whether or not the operation is asterisk. Now, let us determine whether this is. Let's determine whether this is whether it is what closed. Now, solution. For us to determine whether it is closed. Now, the question says that x asterisk y is equal to x squared plus y squared minus 1. First and foremost, s is in R. That means s is in this place. Therefore, x squared is in s squared is in R. Going further, y is an element of R. Therefore, y squared is an element of R. Now, with this, if all these are found in R, therefore, I can further make a conclusion that since all these are in this expression, that is, this particular expression is closed. As far as I carry out my operation and they revolve around this, I can now say it is closed. So you can now say this, that x squared plus y squared minus 1 is in R. Therefore, it is closed, and this is your final answer. Now, commutative properties. Now, a commutative, an operation is said to be commutative if its pattern or if its pattern or change in the mode of arrangement. Now, it is said to be commutative if whenever you change its or rearrange its mode of operation of its element, it does not change the required outcome. That is, it's still the same as the original. For example, if we should have A operation B, it is commutative if it's the same as B operation A. Now, this operation here is said to be commutative because what we have here is obviously going to give us the same with what we have here. For example, if I should say 5 plus 2, it's also commutative as saying 2 plus 5. Now, it is commutative in the sense that it does not change its required outcome. It does not change its required outcome. Either I bring 5 first or I bring 2 first. As far as it gives me the desired outcome, and what is my desired outcome? 5 plus 2 here gives me 7. 2 plus 5 here gives me 7. As far as it doesn't change its outcome, then I can say the particular expression is commutative. There's cases whereby it is not commutative. For example, 2 minus 5 and 5 minus 2. Now, in this case, this is not commutative because this is not commutative. So 2 minus 5 will give me minus 3, and it is not equal to 5 minus 2 or 3. Now, look at this expression is not commutative. So, your binary number has to be commutative. Now, if it's commutative, it's going to pay attention to this particular. Now, example. Now, this is a WAEC question. The question here says, which of the following binary operation is not commutative? So, which of these following can we not reverse? Which of the following is not commutative? Solution. And in this kind of question, you have to test all the whole options. You have to test all the whole. So, you have here that A operation B is equal to A plus B minus AB. Now, you have to reverse it. If it's commutative, then B operation A, what would it give us? B operation here becomes what? B plus A minus BA. Now, if you pay close attention, this is equal. That is, your A operation B is the same as your B operation A. Therefore, it is commutative. Now, you have to test it all through for its options. Now, trying it for B. B says that A operation B here is equal to 3A plus 3B minus A operation B. That is, B operation A here is equal to 3B plus 3A minus BA. Now if you pay close attention, both of them are equal. Therefore, A operation B is equal to B operation A. Now let's go to, therefore it is commutative. Let's go to the C. The C says A operation B is equal to 1 over A plus 1 over B, which is your C. That is, B operation A is equal to 1 over B plus 1 over A. Therefore, if you pay attention, A operation B here is equal to B operation A. It is commutative. Now, let's go to the D. What does the D say? The D here says that A operation B is equal to B minus A plus BA. Now, so B operation A here is now equal to, B operation here is now equal to A minus B plus AB. Now, if you pay close attention, due to the positioning of your plus and minus, this is not commutative. A operation B is not equal to, A operation B is not equal to B operation A. Please pay close attention. It is not equal. It can only be commutative. It can only be commutative if one condition is satisfied. It can only be commutative if one condition is satisfied, and that condition is if and only if A is equal to B. If A is equal to B, then there's no difference between its position, because since they are equal. But here, if B is greater than A, it cannot be commutative. If A is greater than B, it cannot be commutative. Therefore, the answer to this particular question is your D. So D says that what? D is not commutative.
Okay.
Now, associative property. Now, an operation is said to be associative if A operation B operation C is equal to A operation B operation C. Now, if this particular condition is satisfied, therefore it is said to be what? Associative. Now, I can pick up clear examples with numbers. Picking up an example with number, if I say 3 plus 5 plus 2, is it the same with 3 plus 5 plus 2? Now, 3 plus 5 here gives me 8, 8 plus 2, 8 plus 2, 3 plus 5 plus 2 here gives me 7. So 8 plus 2 here gives me 10. It's equal to 3 plus 7 here gives me 10. Now look at, since these two conditions is equal, therefore this particular expression is said to be what? Associative. As far as you can add them in this form, it is associative. Now, don't forget, please, I would like us to note, in associative properties, the arrangement can be said to be immaterial. When I say the arrangement can be said to be immaterial, that is, the positioning can be immaterial. That is, if I position here, changing this 3, the way I change it to this, changed it being in bracket, it can be immaterial. Now, pay attention to this question. A binary operation is defined on set R of a real number by x asterisk y, x asterisk y is equal to x squared plus y squared minus 1. For all x, comma y in R, determine whether or not the operation is associative. Now, how can I determine whether it is associative? Now, pay attention. Don't forget, associative law says that x combination y combination c is the same as s asterisk y as asterisk c. If it satisfies this condition, therefore it is associative. Now, I cannot say, now what this here is, please pay attention, this is the main expression, please. So in this main expression, so let me make my expression for y asterisk c. Expression for y asterisk c is here is y squared plus c squared minus 1. Now this is the combination for it. So here this becomes that what? X asterisk y, so you see here becomes that x asterisk. Now this particular expression here gives me this, that is y square plus c square minus 1. Now at this junction, I cannot pay close attention. Now, so this here is not equivalent to, please pay attention. If you pay attention, because we still have to run this syntax into the main equation. And this is the main equation here. So checking if it's associated, this becomes x. Putting this into this, then this becomes that's x squared plus, now this thing here acts as your y, that is y squared plus c squared minus 1 minus 1. So at this junction, this here becomes that x squared plus y squared plus c squared minus 1 minus 1, and this is now x squared plus y squared plus c squared minus 2. I would like us to note this as what? Equation 1. Now, having noted this as equation 1, I can now what? Proceed. Now, this particular expression is just for this. We're trying to check if this will be equal to this. Now, since we've done that for that, let us go for this particular expression. This one says that x asterisk y asterisk c. Now, x asterisk y will give me this expression, which is x squared plus y squared minus 1 asterisk what? Asterisk c. Now, paying close attention, this particular expression gives us this. Now this one asterisk c, we're still going to put it directly into this particular expression. We'll put it into this expression here. Please, let's pay attention. Now please, okay, let me use my red pen. Is at this junction, I have my square here. Please, I didn't have my square. There should be a square here because of the square form. So this x has its own square. This x has its own square. So this should maintain its own. And at that junction, this should maintain its own square. Then we're going to have our negative 1 as usual. And please note this as equation 1. So pay that same close attention to this. This will be acting as my x, it has in the square. This one here will be acting as my y here having the square. So this becomes x squared plus y squared minus 1 raised to power 2 plus c raised to power 2 minus 1. Now, having solved this, if you pay close attention, this particular answer here is for x asterisk y asterisk c. Why this one here is for the next, which is x asterisk y asterisk c. Now, if you pay close attention, this particular expansion is not equal to this expansion. These expansions, they are not equal. Therefore, we can make a conclusion that says that x asterisk y asterisk c is not equal to s asterisk y asterisk c. So it is not associative. It is not associative, and that becomes the final answer. Now, pay close attention to this question. I'm taking another example here so as to buttress what I've been trying to say, to buttress my point. Now, a binary operation asterisk is defined on the set R of real numbers by, what is it defined? It is defined by P asterisk Q is equal to PQ plus 3P plus 3Q. Where P comma Q is in R, show that asterisk is not associative. Show that asterisk is not associative. And associativity is such that x, y in what R is equal to X operation Y operation R. This is what this condition satisfies our associativity. Now let us say this: P associate Q associate what? X. Is it going to be equal to, is equal to what? P associate asterisk Q asterisk S. Now let us solve for this and solve for this and check if they are both equal. So P asterisk Q asterisk what? X equals to P asterisk Q. What will it give us? P asterisk Q will give us this. That is PQ plus 3 plus 3P plus 3Q in brackets asterisk what? Asterisk X. Now let us pay close attention. Let us pay close attention. P asterisk Q gave us this, right? So this gave us this. Now this, taking this to this as an operation, this is going to give us this is going to give us X multiplied by this, X multiplied by this, that is PQ plus 3 plus 3P plus 3Q plus, it's going to give us this plus 3 of the first, what is the first one here? The first one here says this is the, now listen to me, let's pay close attention. We're going to treat this as two different elements. This is the first element and this is the second element. Now when you put the first element, this is the first, this is the second. When you put them here, it gives us first, second, plus 3 of the first, plus 3 of the second. Now, when I put them first, it gave me what? First, second, plus 3 of the first. So 3 of the first will give me what? This is the first, 3 open bracket, PQ plus 3P plus 3Q. Yes? Then plus 3 of the third, which is Q, which is this, plus 3Q. So therefore I cannot expand this. If expanding this, I'm going to be having, if I should expand this, I'm going to have SPQ plus 3PX plus 3QX plus 3PQ plus 9P plus 9, 3 times 3Q, that's 9Q plus 3Q. So I can go further to collect like terms here. That is SPQ plus, I have 3PX, okay, 3PS, no other 3PS, 3PS plus 3QX. I've satisfied this. I have 3PQ, which other 3PQ do I have? Which other 3PQ do I have? I don't have any other 3PQ, so that's plus 3PQ plus 9P. I have what? 9P plus 3Q. That's going to give me plus 12Q. So therefore this thing here is now equivalent to what? It's now equivalent to what? P asterisk Q asterisk S. Let us go for the other way around. Let's go for the other way. I would like us to what? To note it. Let's note it. What did he give us? So what did he give us? So P asterisk Q asterisk S gave us SPQ plus 3PX plus 3QS plus 3PQ plus 9P plus 12Q. This was what it gave us. Now let us go for its counterpart, which is what? P asterisk Q asterisk S. Now going for that, what I'm going to be having, Just pay close attention. Now, this is P asterisk Q asterisk S. Now, let us do Q asterisk S first. Q asterisk S. Q asterisk S. This one is out for now. Let us treat the one in bracket first. So Q asterisk S. This becomes QX plus 3Q plus 3X. So this is it. So having gotten this as P asterisk Q, put it into the expression to below. P asterisk open bracket QX plus 3Q plus 3X. Now, this is the first element, this is the second element. Don't forget, this is the first element, this is the second, this is the first, this is the second. The first element is what? P open bracket, put the second element. What is the second element? QX plus 3Q plus 3X, plus, what is the third element here is what? 3. What is it? Okay, 3P here, that's the first element, that's 3P plus what? Second element, that's 3Q, that's 3, this is the Q. 3 of Q here is what? QX plus 3Q plus 3X. So at this junction, I have to expand this. And expanding this, it gives us PQX plus 3PQ, expanding plus 3PX plus 3P plus 3QX plus paying attention, plus, okay, we have 3QX plus 3 times 3, that is 9Q, plus 3 times, that's plus what? 3 times 3, that's plus 6S. So at this junction, do I have anything common to add? Let's say PQS, PQ, PX, 3P, QX, 9QX. Nothing is common. Therefore, so P asterisk Q asterisk in bracket S is equal to this long solution here, which is PQX plus 3PQ plus 3PS plus 3 plus 3P plus 3QX plus 9Q plus 6S. Now, if you pay close attention, the associativity is not the same. This associativity is not the same. Now look at what is this giving us. This is having S, let me direct that. This is having SPQ. This is having SPQ, correct? Now this is having PX. This is having PQ. Now they are not equal. They are not what? Associative. So therefore, P asterisk Q in bracket asterisk S is not equal to P asterisk Q asterisk X, and that is your final answer. Distributive property. And so my distributive property says that P comma Q comma R is in R. Is in what? It's a real number. Then what? P times Q plus R. Now this says that here, now the product of P times Q, P times Q, PQ plus P times R, that's PR. Now this is your what? This is your what? Your distributive property. This is your distributive property. Now, so this went further to explain to us that what P times P plus what Q times R, it is not equal to P plus Q multiplied by P plus R. And so this particular expression here is trying to explain to us that what multiplication distributes over addition in R. So whenever you see your sign, the sign of multiplication and addition, you should be you should note clearly that what multiplication will distribute. Now look at this. This particular expression here. This is what addition. Since this is addition, this isn't what distribute. But now clearly your multiplication. Look at this. This is multiplication. So multiplication distributes what over addition in any set of three numbers. So as not just addition, it also distributes over addition and over subtraction. So multiplication distributes over addition, so as it distributes over subtraction. Now, identity element. Now, it's very important. When it comes to binary, you have to talk about your identity element. Now, suppose a non-empty set which is closed. Now, for you to have an identity element, the first criteria is that set must be closed. Your set must be closed. For an identity to exist, that set must be closed. It must be closed under a binary operation asterisk. Now look at this. You have A asterisk E is equal to E asterisk what A, and this is equal to what A. Whatever that satisfies this condition is known as your identity. It's known as your identity element. And one thing is, we should know, your identity is very unique. Under addition, we have identity under addition and identity under multiplication. Now, in layman's definition of identity is a number or variable such that when joined to another operator doesn't change that particular operator. For example, A operation E. This is your identity. Your identity is joined to A. It does not change this operator. It gives us what? A. Or identity of asterisk A gives us A. So identity is a number or a variable such that when it was joined with an operator to any other variable gives you that same variable. Whatever satisfies that condition makes it what? An identity. Now, under addition, what is your identity under addition? 0. That is, every operation added on 0 gives you that same thing. So if I should say Solomon plus 0, Solomon plus 0 will give me Solomon. That is, 5 plus 0 is equal to 5. 7 plus 0 is equal to what? 7. Therefore, 0 here is what? Is an identity. So for your 0 here to be an identity, so under addition, your identity element under addition is 0. Now, going to your multiplication, so your multiplicative identity or your identity under multiplication is, guess what? 1. Why is it 1? It is 1 such that 2 times 1 has to give me 2, 3 times 1 has to give me 3. Now any operation I carry under multiplication on 1 gives me that same operation, gives me that same what? Value. That is, 1 here is my what? My identity. So I believe we've now understood what identity is all about. So going further, your identity is denoted with the sign E. With this sign, this is what you denote your identity with. I believe we are catching it. Now, we have to go further. Let's pick up a wire question from what? Identity element. The question here said, find the identity element E under this operation if the binary operation asterisk is defined by C operation D is equal to 2CD plus 4C plus 3D. If this is the operation, look for your identity. The identity here says that C operation E is equal to what? E operation C is equal to what? C. Therefore, this is trying to tell us that what? C operation E here is now equal to what? C. We call this what? Equation 1. Having noted that this is equation 1, now you take the same step. Now C operation E here, C operation E here, putting your what? E into this expression, putting your E into this expression, it becomes 2CE plus 4C plus 3E. And I'll call this my equation 2. Therefore, paying close attention, equating equation 1 and 2. So equating equation 1 and 2, if you pay close attention to what is happening in this question, now what is happening here? You are going to notice that C operation E and this, we are having the same thing there. Since we are having the same thing there, then we cannot equate them. So equating them now, I cannot say that C here is equal to 2CE plus 4C plus 3E. At this junction, collect like terms. When I say collect like terms, everything that has to do with C should come to one side, everything that has to do with E should come to the other side. So this becomes C minus 4C is equal to 2CE plus 3E. So C minus 4C, that gives us what? Minus 3C is equal to factorizing your E out, that becomes 2C plus 3. So at this junction, divide both sides by 2C plus 3, 2C plus 3. So without doing much, 2C cancels. So E here is now equal to minus 3C over 2C plus 3. And this is your final answer. So I'm trying to tell you this, that you are to have, every question has a unique identity. Now, having this question here, we have its solution. When you say that the operation asterisk is defined on the set of three numbers, A asterisk B is equal to A plus B minus 1 over 2AB for all A comma B in R. Find the identity. Now, identity, don't forget, A operation E is equal to A, which is my identity. I call this equation 1. So putting your E into this expression, it becomes A operation E is equal to A plus E minus 1 over 2AE. Call this equation 2. So since I call this equation 2, what happens? Something is common here. So what are you doing? You are equating equation 1 and 2. So since you are equating equation 1, A here is now equal to A plus E minus 1 over 2AE. So at this junction, you can multiply all through by 2. That is 2A is equal to 2A is equal to 2E minus AE. This is equal to 2A, 2E. So collecting like that, that is 2A minus 2A is equal to 2E minus AE. That is, A minus that 0 here is equal to 2E minus AE. So 0 is equal to factorizing, that's 2 minus A. So at this junction, what? Your E here is equal to 0. So your E here, which is your element, is what? Equal to 0, and that is your final answer. Now, look at this question on tabular identity. It's a JAMB question. It's very, very clear here. That's a JAMB question. So it says the identity element with respect to the multiplication shown in the table. Now we have the multiplication shown in the table. Now, they asked to what? Find what? The identity element. Don't forget, your identity here says that A operation E here is equal to what? A. You should note this. This is the first thing you should note. Whenever you are what? Trying to find your identity, you should what? Note that. Now, you have to come down here and ask, what? That means if I multiply P operation P, what did it give me? R. This is not identity. Okay? P operation Q, which is equal to what? P. Now this looks like an identity. Let us try Q for other variables if it will give us their same value. So Q operation Q is equal to what? Q operation Q is equal to Q. Okay, this looks like identity. This also looks like identity. Let us try for another one. Let's try for S. S operation what? Q. S operation Q is equal to S. It's equal to S. Now with these three, since it has satisfied these three conditions, therefore you can say that what? Your identity here is equal to what? Q. So your identity here is Q. Now another quick way or a very fast way to find your identity is to go to your table and find the corresponding values. Like when I say corresponding value, I mean the value that is arranged in this manner. PQRS, PQRS. So this has to be what? Arranged horizontally and vertically. Vertically what? And horizontally. Now let us go to Q. Is it in R? It is RPRS. RPRP. So it is not arranged well. R here is RRRR. In S here it is SQSR. This you see it's not arranged. But look at in Q here. It is arranged PQRS in Q. You see clearly arranged, and also like this it is what? Clearly arranged. So this is the fastest way to find your tabular identity. Look for the one that is clearly arranged. Once you find the one that is clearly arranged, that becomes your what? It becomes your identity, and my identity here is equal to Q, and Q there becomes your final answer. Now, inverse element. Now this inverse is also very important, just like your identity. Like I said, consider a non-empty set S which is closed under a binary operation asterisk. If S is in S, if X is in S, and if S is an element of the set S, and we can find an element. Now listen to me. So if we have X here as the element, every element in a set has its inverse. So you cannot go about not having its inverse. So every element in a particular set. For example, let us take the wall clock 1, 2, 3, 4, or 5. Let us take the number 1 to 5. Now, 1 here, what is the inverse of 1 under addition? The inverse of 1 under addition here is minus 1. Because don't forget, whenever you bring your element with its inverse, it gives you its identity. That is why this definition is given for inverse, that X operation X inverse is equal to what? Your identity. This is very, very necessary. So whatever you bring in contact, whatever element you bring in contact with its inverse gives you an identity. Now, so 1 here, if I should bring 1 as a number with its inverse, inverse of 1 under addition is minus 1. Inverse of 5 under addition is minus 5. That is why 5 its inverse is minus 5. So 5 minus 5 gives us 0. 0 there is what? The identity element under addition. If you remember when I was trying to tell you about identity. So now, if this is under multiplication now, and inverse of 2 under multiplication is equal to 1 over 2. That is why 2 times 1 over 2 is equal to 1. 2 times 1 over 2, which is the inverse, is equal to, this cancels, is equal to 1. Don't forget what I told you in class. What I told you earlier, what the inverse, the identity under what? Identity under multiplication is 1. Identity under addition is 0. So if I should ask what is the inverse of 5 under multiplication? Inverse of 5 under multiplication is 5 times 1 over 5. That is equal to 5 over 5, and that is equal to 1. Since that is equal to 1, now that is what we have to be very careful, very careful, because that particular hurdle has to be paid close attention to now. So I then say here that what, please, I would like us to be aware of this definition, that what, inverse multiplied by the element, don't forget that having this one that has little comma at the top is the inverse. So inverse multiplied by, so x inverse times s is equal to identity. Whatever thing you are multiplying with its inverse gives you identity. I don't want to know what it is. If I am a, for example, Solomon, as there is what? Solomon's inverse. That is going to give me what? Identity. So please, I would like us all to know this particular definition. Well, it is really what? Necessary. So therefore, your what? Inverse is s, raised to power a comma like this is the what? The inverse of x. And it can also be denoted as a what? X to its negative 1. Now, a binary operation asterisk is defined by this. What is it defined by? Which is the formula? That is what? A asterisk B is equal to A plus B plus AB. For any real number of A and B, if the identity element, look at this, the identity element is 0. The identity element must be given. That is, A operation A inverse is equal to A inverse operation what? A is equal to what? Identity. That is, A here operation what? A inverse is equal to identity, where they say that the identity element is what? 0. I call this equation 1. Now putting inverse into this expression, this becomes A operation A inverse into your expression A plus A inverse plus A inverse. So I can now proceed. Pay attention, I can now call this equation 2. So equating equation 1 and equation 2. So equating here equation 1 and 2, I can now take the step that since this that 0 here is equal to A plus A inverse plus A inverse. So bring this over, that is minus A is equal to A plus what? A inverse. So this here is now equal to minus A is equal to, I can factorize at this end to give me what? A inverse what? 1 plus A. So that if I multiply this, it will take me back to this particular expression. So what am I going to do? Divide both sides by 1 plus A. 1 plus A. So 1 plus A cancel 1 plus A. So A inverse is equal to minus A over 1 plus A. So with this is not where the question ends, but the question wants further to tell us, find the inverse of 2 under this operation. So find the inverse of 2. This becomes that what? 2 inverse is equal to minus 2 over 1 plus 2. So 2 inverse here is equal to minus 2 over 3. So minus 2 over 3 there gives you your final answer. Now, an operation asterisk is defined on the set of real numbers by A operation B. Okay, so your solution directly, that what? A operation B is equal to A plus B plus 1. So if the identity element is what? Note that this is very necessary. So if your identity element is minus 1, find the inverse. Now, so A operation A inverse is equal to what? Minus 1, which is your identity element. You call this equation 1. So A operation A inverse, putting inverse into the expression, that becomes A plus A inverse plus 1. So equating equation 1 and 2. So if you try to equate equation 1 and 2, this becomes what? Minus 1 is equal to A plus A inverse plus 1. So everything that doesn't have inverse, move it to the other side. That's collecting like that. Minus 1 minus A is equal to A inverse. So at this junction, this becomes minus 2 minus A is equal to what? A inverse. Now the question asks you to what? Find the inverse of the element 2 under the. So this thing here, A inverse is equal to minus 2 minus A. This is your inverse. So they say what? 2 inverse is equal to minus 2 minus 2. So your 2 inverse here is equal to minus 4. And that is your answer for this JAMB question that came out in 2001. Question number 16. Okay, now we have our exercise here. We have the number 1, the operation asterisk is defined on the set of real numbers R by this. Then you have to find the what inverse element, and that's the main question. Find the inverse element. So that goes down to the other questions. Here you are to what? This is a while question, and you are given just a theory question. It's a theory question. So you have to read and find what you have to get. And you have another question here which you are told to do what you are supposed to do down to this point. It's a while and echo question. So you solve them and send your solutions to